Okay guys, this is Astronomy Segment 2 notes. Remember that this is the bare minimum stuff. There's so much that we fleshed out in class. This is only for those folks that were absent or need a quick review. This is a bare minimum stuff. So the two overlying questions are how are stars formed and in what way do they change over time, and where is our sun in the stellar evolution. Just a reminder about Cornell notes. The meat of your notes goes here. The side column is really for target words like vocabulary words or an umbrella word that will encompass all the vocabulary words. More for you to sort through, flip through, and then later the summary of your notes. Put in your own words. This is the most vital part of the notes. It allows you to dissect, digest, bask in what you wrote down here in the main beef. Okay, the sun's been fusing hydrogen in its core for about 5 billion years. Okay. It's set to go for another 5 billion years. It has enough hydrogen there to last that long, about 10 billion years. That's a lot. But what will happen, though, when hydrogen finally runs out? Okay? What will happen? So, helium, during this time, has been building up as an ash. It's not fusing. It's not hot enough for helium to fuse. It's a heavier element than hydrogen. So, helium is heavier. Requires more heat, more pressure to begin fusing on itself. But when the hydrogen runs out, okay, fusion will stop in the core. Gravity will win, and the core will collapse because there's no outward push anymore. The fusion had stopped. So that in turn cranks up the heat. When that collapses in, the heat goes way up. Now it's hot enough to fuse helium. So helium is fusing now in the core. The star swells up even bigger. And it will trigger hydrogen fusion just on the outside of that core. Because the hydrogen that was there all along outside the core that wasn't hot enough to fuse is now hot enough to fuse. Because helium puts out a hotter temperature with its fusion. So when we think about balancing act, you have gravity in, pressure, fusion force out. And when they are stable, life is good for that star. But when hydrogen runs out and the core collapses, the temperature goes up and it begins to swell out the star. What happens if the star doesn't have enough mass to trigger the next stage of fusion? Well, the core we know will collapse. It should trigger a hot enough temperature to trigger the next heavier element, but if it's not massive enough, then it will not trigger a hot enough temperature for that next level, the next element to begin fusing. So the whole star implodes and explodes. So the correlation between mass and fusion is pretty much the more massive it is, the more gravity it will have, which will then compress the core, and it will allow fusion of lighter elements into heavier elements all the way, if it's massive enough, it will go all the way to iron, which you can see here. So if it's not massive enough, though, it's going to stop somewhere in the carbon, oxygen, or neon. Just depends on what the mass is of the star. So this is what a star would look like, the core of a star, all onion-like, like with layers of fusion. Each of these elements are just fusing with itself. This is what it looks like right before a supernova of a high-mass star. So a star's mass determines really how many fusion layers it's going to have. Like how many elements, what kind of elements are going to be made. And it's important to note that iron is the heaviest, and therefore when it is reached, okay, and fills the core, it will then be all over for the star. I mean, it's done. It's going to implode and explode in a massive supernova explosion. But there are more elements. I mean, you saw on that last slide here, let me go back. You saw hydrogen, helium, carbon, oxygen, neon, magnesium, silicon, iron. Wait a minute, Miss Polson, that's only what, 3, 6, 7, 6? Elements? Where are the rest of the elements? How are they formed? So that was my next. So that was my next slide here. You know, where are the rest of them formed? Well, the supernova and nova explosions, guys, are crazy. Chaos is happening. Elements are colliding all over the place. Silicon's colliding with neon. Oxygen's colliding with carbon. I mean, they're not fusing with each other. They're fusing with other elements, and that is where the rest of the elements come from. So star life cycle is defined at the stage that a star progresses through over the course of billions of years, and their pathway, their direction, is really based on mass. And of course, mass is going to determine how, where that, how many layers of fusion in the core that are going to develop. So how far fusion will go, pretty much. And here in this picture, and you saw some in class, you start as the star starts as a nebula, and some kind of shock wave moves through and begins to condense the material. Well, condensing material is going to heat up, and it's going to begin to glow. As soon as that reaches a temperature in which hydrogen, being the lightest element, can begin to fuse, now we have a stable star that's burning hydrogen. Or it's not really burning, it's fusing hydrogen. So life is good, all is great, hydrogen's fusing. But once helium begins to fuse, now it's entered into a giant or a supergiant phase. It's now making heavier elements. Helium's fusing into carbon, carbon's into oxygen. Anyways, it'll go and you'll end up with either a planetary nebula, a supernova event, but you end up with these dead cores where fusion is no longer occurring. But again, this layer, the difference between this layer and this layer and this layer is really like which pathway is the star going to go is dependent upon mass. But what about our sun? Where is it in its life cycle and how long will it stay there? So if you figure our sun started in a nebula, went into a protostar and became a fully functioning star that's fusing hydrogen because the temperature was reached in the core because it gained enough mass. It's now just about 5 billion years into its lifespan. It's fusing hydrogen the whole time it's here. But eventually the hydrogen will run out in just the core area. Core will collapse, triggering a hot enough temperature for helium to begin to fuse. When that happens, the star swells, so it becomes now a red giant. Over time, it'll puff off a lot of its mass in the form of nova, and it will form a nebula, a brand new stellar nursery, just like where it started from. What will be left behind is the dead core, no longer fusing, but condensing and seething hot until it, over time, becomes cool. So, this segment also talked about how do we know things about the stars? What do we look at? And you were going through the science behind examining the energy that the stars are emitting. How do you know there are stars out there? Because you see the light. You can detect the light. But it's not just visible light that we can detect. Stars and other objects out there will emit different forms of EM radiation. So in class, we reviewed all of the forms of electromagnetic radiation, starting from, AM radio, to FM radio, to microwave, to infrared, then visible light, and then X-ray, UV, and then X-ray, and then gamma. So those are all forms of electromagnetic radiation, and that's being given off. So when we look at these objects with a different kind of camera that's receiving different types of energy, we can false color these ones here, like infrared. This is heat. These are hot spots that can tell us some things that are happening. What kinds of events would create heat or more heat? What kind of events would create light? We know stars do that, so we can see them here. But what kind of events or areas will create X-ray? That's high energy. So that can tell us, just by examining the different types of radiation, it can tell us a lot about what's going on out there. But specifically in this class, we talk about visible light. So visible light, can allow you to see, yep, you got a cut on your skin, it's reflecting the red light, so you see that it's red, blood is red, blah, blah, blah. X-rays, you get that. X-rays can penetrate the skin and the soft tissue, but it won't penetrate the bones, so you can actually use X-rays to see what's going on underneath the skin for a bone break, for example. So those are examples of reflecting or going through, the energy going through. But what about stars or entities that actually emit some of this stuff? So looking at different EM radiation can tell us different things. But we're going to focus on visible light. So there is a rule. Different elements release different visible light wavelengths, or what we call colors. So the color of light is actually different wavelengths. We talked in class about what a wavelength is. So basically every element, when excited, will emit light. So if we can run some electricity or heat it up enough and put it into a plasma state, it will emit light. And if it's hydrogen, it emits light in this frequency or wavelength and this one. That is the hydrogen, and there's a small one here. That is the hydrogen fingerprint. We call it like a fingerprint. Everybody has their own fingerprint that identifies them. an element has its fingerprint visible light emission frequencies. So this was huge. The fact that we have this catalog of all of our periodic table of elements, and we have all of the emission spectra that they make when they're excited, well, my goodness, stars are made of plasma, they're giving out light. We can then tell what the stars are made of, at least what the atmospheres are made of. We can tell what glowing nebula are made of, just based on the frequencies that we're receiving. Just get a prism, collect the light, fan it out into its wavelength or frequencies, and then you can tell. So it's now possible to tell what makes up the atmospheres of stars and glowing nebula. But now what about motion? So in class we talked about the Doppler effect. Can we detect the motion of stars? When we go out and look at them, they look like they're stuck, they're stationary, they're not moving. And yet they are. They're just so far away that we can't tell the motion. Except for when we look at the emission spectra, then we can see. So the Doppler effect, just as a refresher, is a change in wavelength or frequency for the motion of either the object or the observer. And the Doppler effect can be used really mostly for a toward or away kind of motion. And in physics, you learned it, how it applies to sound. And so there's this example here where this person is listening and hearing an approaching ambulance. The wavelength for sound, when the wavelength becomes shortened, it's a higher pitch. When the wavelength becomes elongated with an ambulance that's receding away from the observer, then it becomes a lower pitch. So this would produce a high pitch when it approaches you, and as soon as it passes you, it produces a low pitch. Well, that's good. For sound, I showed you this image. We talked about what's going on here. This is a moving jet. Okay, it's producing a sound, and in front of it, those wavelengths are moving out in front of it. This is a jet that's not moving faster than the speed of sound, just FYI. So the sound waves are all allowed to move in front of it, and they're squished. So the pitch is higher. When that squished wavelength reaches this person hears a higher pitched sound, but as soon as the jet passes by, you can see these wavelengths are much longer, and the pitch would change. That's called the Doppler effect. And it allows you to see, sense. You can close your eyes and you can sense when the jet passes by you based on this pitch change. But how does that apply to light? So it looks like I'm 12.5 minutes in, so I'm not going to be able to show you this interactive that I showed you in class. But the same thing applies for light, you guys. And there are some great YouTube videos that I can, just let me know, I can pass along the link to you that I've shown in class. So if you were one that was absent, just ask me for those links and you can watch them. But they're very good about showing how the same thing holds for light. But the idea is that, let me go back to this, but the idea that light, when it stretches, I'm going to go back to this. Let's pretend this is light. And by the way, we can't tell light shift on our planet. It has to be exceptionally fast speeds and exceptionally large distances in order to see the change in light. But if there's a star that is approaching you and is putting out light, it's going to shift to a shorter wavelength, which matches the blue frequency. So it turns bluish. And if a star is moving away from you, the wavelengths of light stretch, and therefore it appears red. So red light has a longer wavelength than blue light does. So back to this. So number one, we can tell what stars and nebula are made of by looking at the emission spectra, because every element has its own specific fingerprint emission spectra. Number two, we know the wavelengths shrink when an object moves toward or away. So is it possible to tell, how stars are moving? And absolutely it is, using the Doppler effect. How do we know a star is moving away from us? If they're moving away, the wavelengths are stretched, and they show a red shift. And that is it for this segment. Please make sure you have your Cornell's notes really filled out well, that you've summarized very well, and you've made it work for you.